Okay, so today we're going to talk about basic probability concepts, conditional probabilities, contingency tables. We probably won't get to have time to pivot tables, but I'll post a video for pivot tables. And Bayes' rule is the conclusion of this handout. Okay, so probability. First definition, it's the likelihood that an event will occur. Why do we study probability? Well, we all use probability every day. When you're a baby, you don't have probabilities. When you're born, you don't have probabilities because you've had no experience. But what we've all done over time is we've started to gather information from our surroundings, from our experiences, and we actually develop likelihoods of events occurring. So we use probabilities every day to frame pretty much all of our decisions. So even if you think about when you're turning left, when you're driving, you're considering the probability of getting hit. Now, you turn left based on hopefully a low probability of getting hit, but even then there's no guarantee that that person isn't going to run a red light. So you make a good decision based on the data that you have. That said, you can't guarantee a good outcome always, but hopefully it increases the probability of a good outcome. So this is what we do with probabilities. We're using them all the time. Now, when we're in the business world, the landscape changes at a really rapid pace, as well as we don't have, our formative years of information collection going on. So our ability to collect and synthesize data in that sort of environment, not as good as ours when it comes to looking at a person's face and telling what sort of feeling that they're having or something like that. We can't use that intuition probability the same way. Instead, what we're going to do in that ever-changing world of business is we're going to collect data and be more analytical about it. We're going to determine probabilities based on data, and we're also going to formulate decision-making process to start to eliminate bias using those probabilities, because we all have our biases. Okay, now to start this, we're going to have to brush up our vocabulary. So a little bit of terminology. Mutually exclusive events. Those are two events that cannot occur at the same time. They cannot occur together. So an example would be turning right and turning left. Try it. Good luck. It's impossible. You can't turn left and you can't turn right at the same time. You can do one right after the other, but it's a funky dance. Like, you can't do both at the same time. Collectively exhaustive is a set of events that include all possible outcomes. So continuing from turning right and turning left, is this collectively exhaustive? Does this cover every single possibility? No, it isn't. What am I missing here? Straight, that's right. So you can go left, right, or straight. Those are the directions that one can go in. Now we're collectively exhaustive because we've covered all the possibilities that there are for movement. Now, complement is the opposite of an event. So if I have event A, denoted A, the complement would be denoted as A prime. Or alternatively, I would write A subscript C or A bar. I find A prime is often the easiest to do on a computer. So if I have an event A is right, what would the complement to A be? Left? Is that everything outside of being right? It's left and straight. It has to include everything. It has to be collectively exhaustive. The complement has to cover everything that's not right. Any questions on those definitions? Okay, so here's a Venn diagram. It's those little circle diagrams. So here we have events A, B, C, and D that are collectively exhaustive. They're covering all the possibilities of a set of events. So what events, when you look at these diagrams, are mutually exclusive? B and D, that's right. You can see that there's no overlap between B and D. It's impossible for them to happen together. So B and D are mutually exclusive. Anything else that's mutually exclusive? That's right. So we have in the chat, I see A and D. You can see that there's no overlap. And I heard someone say A and C. There's no overlap there as well. So those would be mutually exclusive. Okay, now what is the complement to event A? When we're talking complements, it's everything that is not A. So it's everything outside of A. That's my complement to A. So if I want to be more specific, what would I write? I could say C and D. And let's be really clear here though. So I have C here. Can I say that B is the complement to A? I can't say B is the complement by itself because there's some overlap. I would have to be more specific and say where it's only B. Okay, where it's only B is outside of A, but not other places because otherwise I'm overlapping with A, which is not complementary. It has to be outside of A. Now, I don't need to include the overlap with C because that's already covered. Now, similarly with D, I have to be careful here. If I say D, I would be counting this portion here twice, wouldn't I? I don't want to do that either. So I'm also going to go with only D, the area outside of C. I don't want to count an area twice. So the complement is only B and C and only D. Everything that's not A is just the, that's my favorite way of putting it because it is complicated otherwise. Okay, so now let's use that in a few simple examples. Let's talk about some dice. Let's say that you roll a 6. Okay, what is a mutually exclusive event to rolling a 6? What other events could there be? You could roll a 1, you could roll a 2, a 3, a 4, or a 5. Rolling any one of those would be mutually exclusive. There would be no, you can't do them at the same time as rolling a 6. Now the complement would be what? What would the complement be to rolling a 6? That's right, rolling anything between 1 and 5. So any one of these is considered mutually exclusive, but when I'm talking about the complement, I have to consider all of those possibilities. Everybody loves feet, right? Let's talk about standing on your right foot only. Okay, so what would be something mutually exclusive to standing on, like doing tree pose on your right foot, standing on your right foot only, no weight on your left foot? What would be a complement to that? There's an obvious one that's a mutually exclusive event. Can anybody think of any other mutually exclusive events? Sitting, yeah, sitting. You could stand on both feet. That's mutually exclusive to standing on one foot, right? Somebody in the other class even said standing on your hands. So you can see that there's a lot of possibilities here. So when I'm looking at the complement here, I have to include all of these mutually exclusive possibilities. I have to include not even mutually exclusive. I have to consider everything that's outside of standing on your right foot. So I'm going to go with Jasmine's approach here, and I'm just going to kind of say not standing on your right foot only. You can make it more generic. One more. Let's talk about this course. This is you studying for the course. So let's talk about passing Babby 8800. What would be something that's mutually exclusive? Mutually exclusive would be failing. That's right. Failing is mutually exclusive to passing. Absolutely. Now, what's a complement to passing? Is it failing as well? Not quite, because one, we didn't include dropping out. You could have had withdrawing from the course. You could have a deferral. I don't know what possibilities are. There's lots of possibilities. So here we would also say not passing. And so I point this one out because we've had some examples before where people are like, but failing, it seems like the obvious opposite to passing. Be careful that you really think about all the possibilities. And if you can't kind of find a way to encompass all the possibilities, like it was easy to with the rolling, then just go with the not. We're going to do some probability rules now. With those Venn diagrams, sometimes we present just the circles, but let's not forget that overall there's other events, like the big possibility. So I'm going to create a big box that encompasses 100% of the possibilities. So here we got the yellow box is going to represent everything that's possible. So I have event A, which is one of the items that's possible. So you can see that it's not 100% likely, maybe 30%, I don't know. And so what we would have, everything that's left over in the yellow box outside of that circle would be considered the complement. So you can see the rule of complements is that the probability of A plus the probability of the complement should add up to 100%. Okay, so there's a visual representation of the rule of complements. And we're going to use these visuals to help us with some more probability rules. So I'm going to add in another item B, another event B, sorry, not item, event B that's also possible. And A and B can happen together sometimes. We have a joint probability. So the term joint probability is when A and B happen together, what that probability is. So that's this probability where they overlap. That would be the joint probability of A and B. Now we have the OR probability as well. Now the OR probability is a little bit different because now we're talking about everything within these circles, A or B. Can you see that? So how can I calculate that? Well, I can look at the probability of A, that would cover this, plus the probability of B. But what's the problem if I leave it there? Remember, we don't want to count the probability twice. And right here in the A and B, we counted it twice. So I'm going to subtract A and B because I counted it twice. So I'm going to subtract it once. So we get this relationship, which is just what I wrote. That's our OR probability. Now we have conditional probabilities. Now conditional probabilities shift the meaning. It's when we're looking at a subset. So really what we're saying is we're going to look and say that A has 100% likely. It's guaranteed to have happened. So if A is now 100%, we don't look at the yellow, do we? This is our new 100%. If A has definitely happened, this is the new 100%. And so when we're looking at the probability of B, when A is guaranteed to happen, that's what this notation implies. What we're looking at here is this shaded portion. So you can see that that was equal to the probability of A and B divided by the probability of A. So we would write it like this. So those are some probability rules that you'll want to know. Now I can rearrange this formula by multiplying up P of A. And I get P of A and B is equal to P of A times P of B given A. Now, if events A and B are mutually exclusive, what we're looking at looks like this. Remember, mutually exclusive means they can't happen at the same time. So what that implies is that the probability of A and B happening together is 0. It cannot, it's impossible to happen together. And so when we're looking at something like our OR probability, now what we're looking at is the probability of A plus the probability of B, either A or B. Now note, before we used to always subtract the overlap, but now since there's no overlap, that's 0, we don't even have to consider it. Now that's only when we're dealing with something that's mutually exclusive. So that's a special rule for mutual exclusivity. Okay, let's get into some applications of this, or an example, I should say. Okay, so Calamity Insurance sells only car and house insurance. Calamity Insurance knows that 10% of its customers will make a car claim and 8% of its customers will make a house claim. 3% of its customers will make a house claim and a car claim. What is the probability a customer will make a house claim or a car claim? A lot of information, so I'm going to try to organize this first. So let's first take a look at 10% of its customers will make a car claim. So I'll start a Venn diagram and I'll have 10% making a car claim. Now 8% of its customers will make a house claim. So now house claims and car claims, are they mutually exclusive? No, you can make both a house claim and a car claim. So we're going to put in some overlap. And we have the house claim is 8%. Now this, of course, is out of 100% of all of their clients. But I'm not showing all of that 100%. Now 3% of its customers will make a house claim and a car claim. So that's going to be this overlap here, the and probability given here. 3% of the customers. So what is the probability a customer will make a house claim or a car claim? So this is our or probability. So what I'm looking at here is all of the areas that we see, both the blue and the red. So I would take the probability of a car plus the probability of a house claim. And then what do I have to do? I have to subtract the overlap. So I get this relationship here. The probability of the car plus the probability of the house minus the overlap because it gets counted twice. So what I get is 10% plus 8% minus 3%, so I don't do double counting. Now, that gives me 15%. Now, if I want the formula, it's simply this formula if you prefer the formula. There you go. Now, what is the probability a customer will not make a claim? Okay, so now we've got our Venn diagram from before, but I'm going to include all the customers now because now we're considering the customers that don't make a claim, which is everything that's left over in the gray area. So now what we're looking at is the probability of no claim is 1 minus the probability of making a claim. It's the complement to making a claim. And we determined before the probability of the claim, it's really the car or house claim is the probability of making a claim, which was determined as 15% in the last part of the problem. So we get 1 minus that 15%, giving us a total of 85%. So this kind of highlights this rule. The probability of neither is 1 minus the probability of either. Neither and either are complementary. Now, given that a customer makes a car claim, what is the probability they make a house claim? Is that this probability right here? Is that what we're asking for? No. Now, this is where a lot of students will end up giving me this value, but let's look at the language here. It's given that a customer makes a car claim. So we've been told the customer makes a car claim. We know that about the customer already. So we're looking at a subset. We're looking at a smaller group. Not all customers are being considered anymore. We're only focusing on this blue group. This is the group that we're focusing on. So let's say for a moment, Calamity Insurance has only 100 clients. Now, that would be a pretty bad insurance firm, but their name is also Calamity. So, they may not, get that much faith. Regardless, let's just look at, for an imaginary purpose, that they only have 100 clients. So if that was the case, the number that made car claims would be 10, right? That's how many would have made car claims. 10% of 100 would have made car claims. That's 10. Now, of that 10, how many would have also made house claims? So that would be this 3% right here. So that 3% would be 3 when we're looking at 3% of 100. So if I want the probability, I'd be looking at 3 out of 10. And you can see that's 3% divided by 10% or 30%. I could just take this 3% and divide it by the 10%, and I'll get the same results. Now I can just go to the formula as well, noting that house claim would be the B in the formula and car claim would be the A in the formula. And I would just plug everything in accordingly and I'd still get 30%. So if you prefer the formula, that's okay too. Okay, now given that someone does not make a car claim, what is the probability they will make a house claim? Okay, so now we're saying don't make a car claim. So we're looking at everything outside of this black spot. Everybody that does not make a car claim. So it's not just the gray area. It's the gray area and the red area that's outside the black spot. Now, everything outside that black spot is really the complement to making a car claim. It's those that don't make a car claim is 90%. Because car claim was 10%. So we're looking at that remaining 90%. And what we're interested in is of this, how many make house claims? So we're looking at this wedge of that red circle. So that wedge of the red circle is what? The red circle itself was 8%, and this portion of the red circle was 3%. So I'm left with 5% in that wedge of red circle. So the probability of H and no car claim is 5%. And so now I'm going to get the conditional probability. If you want the formula, here are your references. And I would have 5 out of 90, or 5.556%. Okay, so now are making a car claim and making a house claim independent events? Explain using statistics. Now there's a new term. I'm just going to leave that as question marks, and we're going to go back to terminology, and we're going to talk about independent versus dependent. Okay, so I'm going to introduce terminology that is used in the textbook. These are all concepts that you learned in business statistics, but the language might be slightly different because it's more technical. It's what it's technically called, which we don't always use when we're teaching business stats. So a prior or simple probability is the probability of an event without consideration to anything. It's just your basic P of A. It would have been the probability of a car claim, the probability of a house claim, not considering any other events. Now, a posterior probability is just a conditional probability, and I'll use those terms back and forth. In fact, I'm more likely to say conditional probability, but the textbook will sometimes say posterior probability, and in your homework, it might say posterior probability. So this is our conditional probabilities. So given that A has already happened, or that it's guaranteed to happen, a subset, what is the probability of B? Sometimes it changes, sometimes it doesn't, which leads us to what independent probability implies. Now, an independent probability means that the probability of B does not change if A occurs. In other words, A has no effect on the probability of B. If A has already happened, what's the likelihood of probability of B? It's the same as it always was. So as an example, I sometimes bring in football at this time of year. What's the probability of Florida winning the Super Bowl? Well, will it change if I get hurt? No, they're completely independent events. I have no effect on that team and Tom Brady's abilities. It relies heavily on Tom Brady getting hurt. It would be dependent on that, but it would not depend on whether I got hurt. The probability would stay the same. So A, if Nilu gets hurt, what's the probability of B? It stays the same as B. Now, that said, dependent probability means that it changes. That probability would change. So what's the probability of B of A? It's not going to be the same. That probability is going to change. So this would be if Tom Brady gets hurt, then that probability would change substantially. It would be very, very low. Okay, so let's do a couple of examples to illustrate these concepts that aren't football. So you have coin A and coin B. You flip coin A and then you flip coin B. Are the outcomes heads or tails of coin A and coin B independent or dependent? Well, let's look at this. If I flip coin A, what's the probability of it being heads? It's 1 out of 2. P of heads for A. Okay? A heads. That's what that AH stands for. Now, here, what's the probability before flipping coin A of it being heads? It's 1 out of 2. Right? Now, I flip coin A and I get heads. Now, what's the probability of coin B being heads? Does it change? Okay, so I flip coin B, and the probability of this coin being heads, given that A was also heads, it doesn't change. It's still 1 out of 2. Makes no difference. Thus, we would say that the events are independent. The probability doesn't change. Let's do another example, drawing a card. And I think you can guess already the first one was independent. What's this one going to be? Okay, so you pick 2 cards, A and B, from a deck of 52 cards. Is the probability of card B being a king dependent or independent on card A? All right, so let's look at this. I have a deck of cards. I grab card A. And the probability of it being a king is going to be 4 out of 52. And that's the same thing as the probability of the card B being a king before, right? Just going to be 4 out of 52. Now it's a king. So what's the probability? And there's 51 cards left. What's the probability of card B being a king? Well, there's 3 cards that are kings that are left. So I have 3 out of 51. So you can see that the probability has changed from 4 out of 52 to 3 out of 51. So the probability of card B being a king changes based on really just flipping card A or drawing card A first. The probability changes. Now, if that's not convincing, even if it wasn't a king to start with, I would still have 51 cards left. Card B, sure, it would be 4 left for the kings, but it would be 4 out of 51. The probability still has changed from 4 out of 52 to 4 out of 51. Regardless of what card A is, the probability of there having a king, just because there's 51 cards left, it's changed no matter what. So you can see that they'd be dependent. So to summarize, when you have dependent events, the probability of A changes when B happens, when B is guaranteed to happen. Alternatively, you could look at the probability of B and say it changes when A happens. Doesn't matter which way you look at it. But please note that the probability that we're interested in is always in the front. Just so you can kind of get that notation clear. Now we get our conditional probability with this formula, and it can be rearranged to give us probability of A and B, the joint probability like this. Now for independent events, those probabilities, when we have a condition, they don't change. The probability does not get affected. Likelihood doesn't change. So now with that in mind, what happens here, you can see that P of A is equal to P of A given B. So when we're dealing with independent events, the probability of P of A and B is probability of A times probability of B. So this is only if you can show that it's independent. And you have to be able to show that it's independent to be able to do that, or have some evidence that they're independent events. Now, be careful here that independent is not the same as mutually exclusive. I think when we talk in layman's terms and conversation, sometimes we use the words for the same purpose, but they're very different meanings. In fact, we don't even study independence when we have mutually exclusive, because ultimately, when you're mutually exclusive events, they can't happen together. They cannot happen together. It's impossible. So we don't care about it, like the conversation of independent or not. It's kind of moot. It doesn't really matter. We're not talking about a probability changing. We're talking about a probability becoming impossible. It's impossible. So when we're talking about mutually exclusive, the probability of B given A is 0. The probability of A and B is equal to 0. That's mutual exclusivity. But when we're talking about independent dependence, we're more interested in what kinds of shifts. What is the impact of one on the other, one event on another? So far I've shown how to do these probabilities with Venn diagrams, but we're not really going to be using Venn diagrams in class. You might have them on the paper, on the side. Fantastic. But what we'll be using is Excel, in which case tables are far more valuable. And a contingency table is essentially taking that Venn diagram and putting it into a table instead, where all of our overlapping bits are on the inside. All of the ands are on the inside. What we're going to do is we're going to look at contingency probability tables. a table that lists the various events and combination of events and their associated probabilities. So when we make a probability table, any probability table, we have two variables that we're considering. You don't really need a table unless you have two variables. So variable A might be something like house claim or no house claim. So when we look at those, we would put those events as one heading, and then we would have another variable, something like car claims, no car claims. And that would be our other heading. Now, this is really important. Variable A, that house claims, no house claims, they have to be mutually exclusive. There can be no overlap whatsoever. No overlap whatsoever. They have to be mutually exclusive items, and it has to be collectively exhaustive. It has to cover everything. And that goes the same for the row headers, our B, variable B. Now, on the inside of a contingency table are our joint probabilities, the and probabilities. And on the outside are our prior probabilities, things like the probability of a car claim, the probability of a house claim, not considering anything else. There's no combinations. And that goes the same for the bottom of the rows. And then everything on the inside of the table should total up to 100% or 1. So let's put this to our insurance example. So Calamity Insurance sells only car and house insurance. We're going to create I'm going to get into the details in a second, but first we're going to start setting up the table. We're going to create a contingency table for the problem. Remember, with the contingency table, the last row and the last column are totals. So now with the row headers, they have to be mutually exclusive and collectively exhaustive. So imagine I start with car claim. What would be mutually exclusive to car claim? A house claim. Not quite. Let's think about that. Can you have a house claim and a car claim at the same time? Yeah, you can, right? So that's not mutually exclusive. What it would end up being is the no car claim. So now we have mutually exclusive and collectively exhaustive. It's covered everything. Now here's where we would put house claim. And what would be mutually exclusive to house claim? Would be no house claim. We check, is it mutually exclusive? Yep. Is it collectively exhaustive? Yes, we've covered everything. So now what we're going to do is we're going to start filling in the spreadsheet. I'm going to do it in the PowerPoint, and you're going to do it in Excel. And we'll go back and forth. And when you're doing this in Excel, only type in any values that you really have to. Wherever you were doing a calculation, I'm going to ask that you reference cells. So use equal to and then reference the cells like you would in BSIS. So now when we're doing this, what we can see is that we have 252,900 clients. Where would that go in my contingency table? That's right. That would be the grand total in the corner. This is 100% of all your clients. So it goes right there, 252,900. Now the next piece of information we have, make sure you're putting this in your spreadsheet while we go, is 20,232 have made a house insurance claim. So where would that go? That's right. That's a total number. This is not a joint probability. It's not both car claim and house claim. It's just those that made house claims. 20,232 in total. Similarly, 25,290 in total have made car insurance claims. So that's going to go at the end of the row for car claims. Finally, we have 7,587 that made both house and car insurance claims. Where's that going to go? Because that's where we see car and house intersecting. So that's going to be where we have both car and house claims. Now from here, we should be able to use some math to solve for everything else. So what you're going to do in your spreadsheet is for this cell, for instance, you're going to have is equal to, the row here should total up, these two elements should total up to be 25,290. So I'd take 25,290 minus 7,587, giving me 17,703. Now, similarly, for these two cells should total up to give me 252,900. So I would write equal to 252,900 minus 25,290, giving me 227,610. And I would continue to fill in the cells accordingly. So I'm going to let you do that. And what you should get at the end is this. This is a contingency table, but what's more useful than these values are probabilities. So we're going to use this table to create a contingency probability table. So we have the same structure for the table, but now we're going to create probabilities. And let's remember that when we have a contingency probability table, this will be 100%. So everything is in relation to 252,900. So for this cell, for instance, I would have 7,587 divided by 252,900. And that would give me 3%. For the next cell, I would have the 17,703 divided again by our grand total of 252,900, giving me 7%. And even on the total rows, I would have the 25,290 divided by 252,900, giving me 10%. And I would do that for the remainder of the cells. Now, a little reminder when you're working in Excel, because I'm dividing everything by the same value, I'm taking 7,587, dividing it by 252,900. I'm dividing every single cell by the same value, so I can lock that ladder reference in. Using F4, I can have dollar signs on that. And then I can just drag it through everything. And every cell is being divided by 252,900 by locking in that reference. Okay, now we're going to use this probability table to answer some questions. So we're going to determine the probability a client makes a house claim. So for house claim, I would be looking at the total probability of a house claim of 8%. And so that would be P of house claim is equal to 8%. Now you have this question in your spreadsheet, so you reference that cell. And so you want to do cell referencing because in the real world, your data is going to change. You're going to get updates on your data. And so you want to only have to change the inputs that have changed, and everything else should just flow. And if you don't use equal signs, that's not going to work out. Okay, our next question is, what's the probability a client makes a car claim? That's again a total. That's not a joint probability. So we got the prior probability of 10% here. The probability a client does not make a car claim. With the contingency table, no calculation is necessary. I just take that row and I take that total. The probability of no car claim is 90% as well. And now we have a probability a client makes both a car and a house claim. Well, that one is a junction. We've got car and house claims. Just remember, the and probabilities are on the inside of the table. So I look for where house and car intersect over here at 3%. So I get car and house claim. The probability is 3%. Now, what is the probability a client makes a car or a house claim? There's two ways I can approach this. I can first look at just inside the table and those cells there. That's car or house claim, isn't it? So I can just add them up. So I have the probability a client makes a car or house claim would be 3 plus 7 plus 5 is equal to 15. Doing that addition is really easy when you're dealing with a small contingency table. But if you had a big contingency table, that might be a pain in the butt. So another way you could do this is we could look at the totals. I know that I've got 10% in total and 8% in total for the house claims. But then I would also have to subtract the overlap. So that would be 10 plus 8 minus the overlap of 3%. And I get 15%. And that's our formula. Now determine the following probabilities. The probability that a customer who has made a car claim makes a house claim. Now, as we noted when we were using the Venn diagrams, this is a conditional probability. The customer has made a car claim. We're not looking at all customers. We're looking at a subset of customers. So using my contingency table, I can do it visually by isolating car claims and ignoring everything else. This is my new subset. This is the new group I'm interested in. And this is my new total. I have a new total of 10%. So the probability of a house claim given a car claim, my total of 10%, it would be the 3% of that made the 3 out of the 10 that made the house claim. So it'd be 3% divided by 10%, and I get 30%. So I think you can see, I hope many of you can see the visual aid that the contingency table provides here, if you just block everything else out. Now, if you prefer the formulas, go ahead and use them. You can use the formula as noted here. Now, is the probability of a client making a house claim independent or dependent of the probability of a client making a car claim? Now we're going to answer this question. So this is the information we've collected so far. And let's remind ourselves of our definition of independent and dependent. So I'm going to test for independence. I'm going to see if this independent statement holds up. If it's independent, the probability of a house claim doesn't change under the condition of a car claim. Alternatively, I could look at it as the probability of a car claim should not change, and this should be written as house claim, if there was a house claim. So either of these approaches would work. I just got to choose one of them. Now, with the information I already have that information, so I'm going to use it. I'll leverage the information I already have, and I'm just going to use the first statement here. But I could have gone and examined it the other way as well, and it would have been just as legitimate. So now I know that this is 8% and 30%. We can see that they are significantly different. In real life, don't expect them to be exactly the same, but this is substantially different. So it is not independent, and we can conclude that it's dependent. So what I've just introduced is a contingency probability table, but that's not the only type of probability table that we have. We also have conditional probability tables. Now with the conditional probability on the inside, instead of the and probabilities, we have conditional probabilities. And what you're going to find is that in this case, you can see that the conditions were all the A events. So that was our condition. So the total for each condition of A totals up to 100%, because we're looking at a subset of A1, one row. It's its own subset. Each row is its own subset that you can almost examine independently. So using our using our contingency table here, we're going to create a conditional probability table. So the condition I want to focus on is going to be car claim or no car claim. So to do that, I'm going to first focus on what if there was a car claim? What is the probability of there being a house claim or no car claim? So I ignore everything that's not a car claim. Ignore everything else. And we have a new total of 10%. So the probability of having a house claim, if you've already had a car claim, is going to be equal to 3 divided by 10. The 3% divided by the 10%, giving me 30%. Okay, and you do that in your Excel as well right now. Now, for no house claim, I would have the 7%. divided by the 10%, giving me 70%. And it should total up to 100% of the possibilities, because the condition is a car claim, meaning if a car claim has definitely happened, if it's 100% likely, what is the probability of a house claim? What is the probability of no house claim? Should always total up to, the condition row should total up to 100%. And then we're going to do the same thing with no car claim. Ignore everything else, both tables. What you have is your 5 divided by your new total of 90, and your 85 divided by your new total of 90. You should get 100. So that's with the condition of car claim or no car claim. But you can also have a condition of house claim or no house claim. We're not obligated to make it work out in rows. You can also do the same structure with the condition as a column. Now, when we do that, we're going to isolate house claim as our new condition and ignore everything else in both tables. Now our new total is going to be 8%. And you can say the probability of a car claim given a house claim is going to be equal to 3 divided by 8, or 37.5. And similarly, when I'm looking at no car claim, I would have the 5 divided by the 8, or 62.5%. And if I total up, this should validate that it's 100%. I would do a similar exercise with the next column, no house claim, ignore everything else. I'll get 7 out of the new total of 92, 85 out of the new total of 92. And that column should total up to 100%, because we're isolating a subset of no house claim. That's our new 100%. So the next thing we're going to do is we're going to do a new example. So that's going to be the Q2 worksheet in your spreadsheet. So after the American presidential election in 2020, an NPR PBS NewsHour Marist poll had the following results to the question: do you trust that the results of the 2020 elections are accurate or not? Now, this is based on a real poll, but I did manipulate the data a little bit. So it's based on a real poll, though it's not exactly the poll results. Okay, so is the above table that you're presented here a contingency probability table or a conditional probability table? So this matters when you're reading probabilities, especially when you're reading news information. Know whether it's going to, what kind of probability you're reading. It's really relevant as in terms of your interpretation of the material. So is this a contingency table or a conditional table? Almost everybody in my sets have been saying contingency. So I'm going to remind you of a rule for contingency table, is that all of the joint probabilities on the inside should total up to 100%. When you look at this, does everything total up to 100% on the inside? No. Now, do the rows or the columns total up to 100%? Well, this row totals up to 100%. 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 So we can say that this is a conditional table where our conditions are the party identifications. What this poll is telling me is that if a registered voter is a Democrat, they're 95% likely to have said, yes, I trust the election results. They're 3% likely to say, no, I'm not sure they're accurate. And 2% likely to be unsure. And it kind of makes sense. If they were a Republican, it would have been a 24%, 72%, and 4%. Do those results really surprise you? That there are some partisan lines to those opinions on trusting the election? Not so much. I think we all know that there's some partisanship going on there. So this is a conditional probability table, and the condition is party identification. Now we're going to use these results to answer some questions. Okay, so now with that in mind, we also are given this information. 36% of the registered voters they surveyed were Democrat, 28% were Republican, 34% were independent, and 2% identified as other. So using all of this information, I'm going to ask you the question. What percentage of registered voters trust the election results are accurate? Do not trust them or are unsure? Essentially what I'm asking you is what percentage said yes out of everybody that was surveyed, all the registered voters that was surveyed. What percentage said yes to the survey? What percentage said no and unsure? Now, from this table, you can't tell, can you? Those prior probabilities aren't in conditional probability tables. They're in contingency tables. Those are what are on the edges of the contingency tables. So we need a contingency table, and that's what we're going to do. So in our last example, we took a contingency table and we created a conditional probability table. This time we're going to work in reverse. So first I'm going to take this new information that was given to me, and I'm going to put it into the table. 36% of all of those that were surveyed were Democrats. 28% identified as Republican, 34% identified as independents, and 2% identified as other. So those are totals. That should total up to 100% of my voters, of my registered voters, I should say. Now, the next thing is I'm going to try to fill in the inside of this table, because what my main objective here at the end, that's going to tell me the probability of yes, the probability of no, the probability of uncertain. That's my main target. But first I need to fill in the inside of the table. And let's remember that these are my and probabilities, not conditional probabilities and probabilities. Remember that with the conditional probability table, I use this formula right here. So I can transpose that to get an and probability. And that's the formula I'm going to use if you want a formula. I'm also going to show you how we can do this a little bit more intuitively using our logic. So I'm going to isolate one group at a time again from the conditional table. So the conditional table, note that the conditions are horizontal, they're in the rows. So I'm going to isolate one row at a time. So first I'm going to look at the Democrats. And I'm going to say 95% of Democrats. Well, we had 36% Democrats. So I would say 0.95 times 36% of the Democrats. And then that would give me my percentage of the ands. So that would give me 34.2%. Note that we are now multiplying. When we go from a contingency table to a conditional table, we divide. When we go from a conditional table to a contingency table, we multiply. Now I would say 3% of the Democrats, or this 36%, said no. So that would be 1.08%. And at 2%, 0.02 times 36, or 0.72%, we're unsure. So that's how I would do the first row. Then I would isolate it one row by row. So you can see here, now I would be looking at this row, and I'd be getting these results: 24%, 72%, and 4% of 28. And I'll let you fill in your table as such. Now, once you've filled in the inside of the table, you can sum up each column: 64.1% for yes, 31.3% for no, and 4.6% for unsure. And this gives us the answer to our question. What percentage of registered voters trust that the election results are accurate? 64.1%. Trust said yes, I trust that the election results are accurate.